Hello everyone. This lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is mathematics class, semester 3, calculus paper 1. So maths 1, calculus. So in this lecture we will start unit 2, that is indefinite integral and improper integral. And improper integral. So let's define some of the terms. So first definition, that is indefinite integral. Let f is from close interval a comma b to r be Riemann integrable function then the function g of x defined as integral a to x f of t dt is called as indefinite integral of f on close interval a comma b. So let us have some example based on this indefinite integral. So the question, if f of x is equal to box x for all x belongs to close interval 0 comma 2, find indefinite integral of f. Solution. So f of x is box x function, so that is greatest integer function, so it is 0 if x is between 0 to 1, it is 1 if x is between 1 to 2, and it is 2 at x is equal to 2. So let's find out the indefinite integral of this. So if x is between 0 to 1, then my g of x is basically integral 0 to, so in this case you can see g of x looks like a to x here. So x is variable and a is a starting point. So here in this case my a is 0. So 0 to x f of t dt. Now where does x belongs? X between 0 to 1. So when x is between 0 to 1, In that case, my function f of x is straight away 0. So I should write down here, it is 0 dt. So it is integration is 0. Now if x is between 1 to 2, then again we will find out g of x. So g of x is integration 0 to x f of t dt. Now when I say 0 to x, but my x is between 1 to 2, so I should split this. So it is 0 to 1 f of t dt plus 1 to x f of t dt. 0 to 1. Between 0 to 1, my function is, if x is between 0 to 1, my function is 0. So my f is 0 in that case, plus 1 to x. Now where does x belongs? X between 1 to 2. Between 1 to 2, what is my function? If x is between 1 to 2, my function is 1. So I should write down 1. 1 times dt. So if I integrate this, then 0, it will be t, and t will be replaced by x minus 1. So the answer is x minus 1. Now case 3 is if x is between at 2. So if x is 2, then again we need to find out g of x, which is a to x. A is 0, x f of t dt. Now this x will be replaced by 0 to 2. Now here x is very specific, f of t dt. Now this 2 will be replaced by 0 to 1, f of t dt plus 1 to 2 f of t dt. Between 0 to 1, my function is 0, and between 1 to 2, my function is 1. So integration of 1 is t. T goes from 1 to 2. So 2 minus 1 is 1. So what my g of x is equal to 1 if x is equal to 1. So in all, I can write down now my g of x. So g of x is equal to, it is, in first case we got it as 0, in second case we got it as x minus 1, and in third case we got it as 2. X minus 1, 2, and it is 0. So if x between 0 to 1, if x is between 1 to 2, and if x is between 2. Okay. So indefinite integral of f we have easily calculated, it is not difficult. Let me have one more example. So there could be an homework example. You find out the indefinite integral if f of x is equal to box x and x belongs to 0 to 5. This is very simple, so I'm not doing anything. So second example which I'll take is, again find out the here it is find g if fx is this. So again find g. So g of x, that is indefinite integral. So if my f is given as follows, if my f of x is given as mod x for all x belongs to -1 to 1. Now it's very clear that we can write down fx and is in following way. So mod x means it is either x or minus x. So x if x is positive and minus x if x is negative. So negative means it is x must be between -1 to 0. You can add 0 anywhere, that doesn't matter, and it is positive if x is greater than equal to 0 and less than equal to 1. So this is how my f of x is defined. Now I need to find out the indefinite integral of f of x. So well, we should start with the internal interval. We will start with -1 to 0 first and then 0 to 1. So let us have the cases. So if x between -1 to 0. Right. So let me write down g of x in that case. It is integral a. In this case my a is -1. So it is a to x f of t dt by the definition. But what is a? -1 to x f of t dt. Now x is again we can check out x is between -1 to 0. If x is between -1 to 0, my f of x is minus x. But I want f of t. So f of t will be, instead of x we will write down t. So -1 to x, it is minus t dt. And the integration of minus t will be minus t square by 2 -1 to x. It is minus x square by 2 minus plus 1 by 2. So what I got is as follows: 1 minus x square divided by 2. Right. So let me explore the another case. If x is between 0 to 1. So in that case I need to find out my g of x. G of x is again a to x, that is -1 to x f of t dt. But x is between 0 to 1, so I need to have that 0 to 1. So what I'll do is -1 to 0 f of t dt plus 0 to x f of t dt. Now between -1 to 0, my function is very clear. It is minus t dt plus 0 to x, and x is again 0 to 1. So it's a positive function. So it is f of t is t dt. So let me integrate this. It is minus t square by 2 -1 to 0 plus t square by 2 0 to x. So it is 1 by 2 plus x square by 2. So finally we got x square plus 1 upon 2. So my final g of x, that is indefinite integral, is 1 minus x square by 2 plus x square if x between 0 to 1, and it is 1 minus x square upon 2 if x is between -1 to 0. Right. So here is a quick homework for you all, and I'm sure that you will definitely do this. So the homework is as follows. Find gx if f of x is given as -1, 0, 1, if x is between -1 to 0 at x is equal to 0 and at x greater than 0 less than equal to 1. And here the answer is also given, so let me note down the answer also, which will help you to get the answer, or maybe answer will help you to understand in better way. So answer is, it is minus 1 minus x if x between minus 1 to 0. It is minus 1 if x is equal to 0, and it is x minus 1 if x is greater than 0 and less than equal to 1. So let's see, if you did not get the answer, then definitely I will discuss this in class. Now there is a nice property about this indefinite integral. So indefinite integral is always continuous. So this is one of the important theorem of a calculus we will prove now. So theorem is, let f is from closed interval a comma b to r be Riemann integrable function, be a Riemann integrable function, integrable, and g of x is given as integral a to x f of t dt for all x between a to b. Then g is continuous, on closed interval a comma b. So let's prove this. So let's write down what is given. So it is given fact 1, f is Riemann integrable. So if it is Riemann integrable, then definitely it is going to be bounded. So this would imply f is bounded on closed interval a comma b. And if it is bounded, then we can always found a bound. So this would imply there exists a constant m belongs to R such that modulus of f of x is always less than m for all x belongs to closed interval a comma b. Let me call this as 1. Right. So what I wanted to prove is as follows: to prove that g is continuous. G is continuous on closed interval a comma b. So how will I prove g is continuous on closed interval a comma b? The idea is, take an arbitrary point from the closed interval a comma b and show that the function is continuous at that arbitrary point. And if it is continuous on arbitrary point, implies that this function is continuous on closed interval a comma b also. So let p belongs to closed interval a comma b be an arbitrary point. That is an any point from closed interval a comma b. So our aim is to prove that g is continuous at p. Right. So what I need to prove that is limit as x approaches to p, g of x should is equal to g of p. This is what I wanted to show. Or in other words, we can show that for every epsilon greater than 0, there exists delta greater than 0, such that mod x minus p less than delta would imply g of x minus g of p less than epsilon. Right. So these are the one of the way to prove this. What I'll do, this whether this x approaching to p, suppose this is my AB and this is my p. So suppose I approach x from the left hand side and similarly from the right hand side. These are the two cases we will explore, and in the both the cases we will show that mod g of x minus g of p is always less than epsilon. Right. So what I'll do, so for any epsilon greater than 0, so assume that epsilon is always 0. So take case 1. If my if I'm approaching from the left side, so that means x is less than p, so I'm approaching this side, so my x is like this. So if x is less than p, let's say less than equal to p, so this would imply mod x minus, or this would imply x minus p is always less than equal to 0. This would imply if the number is less than equal to 0, then modulus of x minus p is basically minus of x minus p. Okay. And what I'll do is as follows. I will say choose delta greater than 0, or maybe I will say delta as a timing, I'm writing it as in blank or dot dot, right? And we will prove that with this delta we have to prove that if mod x minus p less than delta implies mod g of x minus g of p is less than epsilon. Okay, so this is what, so suppose we are assuming that x minus p less than delta, and we will prove that mod g of x minus g of p is less than epsilon. So let me consider this part. So consider modulus g of x minus g of p, right? So it is also given that g of x is an indefinite integral, right? So how the g of x is defined is very important. So it is a to x f of t dt. Right. So let me write down that. Modulus g of x is a to x f of t dt minus g of p will be a to p f of t dt, right? But this p between a to x, a to p, there is a x. So what I'll do is this is equivalent to saying that integral a to x f of t dt minus a to x f of t dt. I could say this is plus, I'm adding x into it because between a to p there is x. This bracket complete and mod is also complete. Now you could see that this term and this term will get cancelled. So what I left it with is as follows. So I will have minus integral x to p f of t dt. But this minus of modulus is same as that x of p f of t dt. That's fine. That's a modulus property. But f is R integrable, so mod f is also R integrable. So this modulus can be taken inside, and this says that it is integral x to p modulus of f of t dt. The reason is, since f is R integrable, implies mod f is R integrable. Further, we know that this mod f of t is less than my m. Somewhere I have written number 1, I guess, yeah. F of x is less than. So this is less than equal to integral x to p. This is m times dt. And this is same as if I integrate this m, then this is p minus x. What is p minus x? Somewhere I have written. Yeah, this is p minus x. So p minus x is x minus p basically, modulus x minus p, which is same as m times mod x minus p. But I know that my mod is x minus p is less than delta, since mod x minus p less than delta. Now I can choose delta in such a way that I want this mod g of x minus g of p should be less than epsilon. So it is very clear that I should choose delta as here m times, I should choose it as epsilon upon m, so that I will have epsilon. So what I got is as follows: g of mod g of x minus g of p is less than epsilon, provided mod x minus p less than delta. So here I have kept a space, that is m upon epsilon, and we should make sure that m is positive. I hope I have written. So I should say there exists m belongs to R plus such that m must be positive now. That such m is always exist, right? So what we got, therefore we got mod g of x minus g of p as less than epsilon whenever mod x minus p less than delta. So this would, in this case, it shows that g is continuous at p. Now let's prove the case 2. Case 2 says that if I approach x p from the right hand side, right? So something like this is a, this is b, this is p. I'm approaching p via right hand side. So what does this imply? This implies x minus p is greater than equal to 0, and this would imply mod x minus p is same as mod x. This says that mod x minus p is x minus p only, since it is positive, right? So now we can again say that for epsilon greater than 0, choose delta greater than 0 such that delta we supposed to write, right? And what we want to prove is as follows. So we want to prove that for every epsilon greater than 0, there exists delta greater than 0 such that mod x minus p less than delta would imply modulus of g of x minus g of p less than epsilon. This is what I wanted to prove. So let me consider modulus of g of x minus g of p. So we know what is g of x. It is a to x f of t dt minus integral a to p f of t dt. Now you can see that where does my x belongs now here? My x is p is between a px. So now I should split here. So what I will have is as follows: a to p f of t dt plus p to x f of t dt minus a to p f of t dt. Now you can observe that this term will get cancelled and I'm left with p to x f of t dt. Now again f is R integrable, so modulus of f is also R integrable. So according to mod, this will be less than equal to and this will come inside. So since f is R integrable, implies mod f is R integrable. Now, but I know star says that mod f is less than equal to m, so p to x, this is m dt, and this integration is m times mod x minus p. But x minus p is basically mod x minus p because we have already stated at very beginning only. So yeah, x minus p is same as mod x minus p. So I can make it as mod x minus p, and we know that mod x minus p is less than delta. So while choosing delta, we should write down delta is equal to m upon with the epsilon upon m. It is epsilon upon m. On the same, I think in case 1 also I have taken epsilon upon m. Yeah, I should write it is epsilon upon m. So epsilon upon m. So it is epsilon, because if I write delta as, so epsilon upon m, so it is epsilon. So what I proved is as follows: therefore modulus of g of x minus g of p less than del epsilon whenever mod x minus p less than delta. So from case 1 and 2 we could show that g is continuous at p, and p is arbitrary point, so p can move over entire AB, so hence g is continuous on closed interval a comma b. So therefore from case 1 and 2 g is continuous on closed interval a comma b. So we have proved a very important property now, that indefinite integral is always continuous. Thank you.